Greetings and welcome, friends. Today, we're going to continue our look at solving things, I guess. That sounds good. And we're going to start solving some inequalities, not just plain old equations. What do you know? But starting off, I want us to actually recall something, right? A review, something coming up from the past. So let's recall the following. What if I asked you to graph the following? X is less than 2. And I guess specifically I'd have to say that I'm having you graph this in one dimension, because this actually can mean something very different in 2 dimensions. So if I was graphing this, so what I would do is draw a plain old little number line, right? And I've got, in order to graph this, I don't actually look for too much detail, just the significant stuff. It's good to know where 0 is, right? And let's see, 2 seems to be significant here, so I'll tell us where 2 is. Maybe I'll throw in another tick mark or 2 in there, but you don't even have to do those. And let's see, I'm talking about all of the values of x that are less than 2, okay? So what makes this true? Does 0 make this true? Is 0 less than 2? Yeah, so 0 would be a solution. Does 1 make this true? Yes. Yep. Would 1.5 make it true? Yeah, like 1.5 would be like here-ish. That would be true. How about like 1.9?
Yep. Yes.
Yeah, how about 1.99?
Yep.
No.
Yeah, it would.
Yeah, that's fine. It's less than 2. What about 1.9 repeating?
No, that's what I thought.
Oh, because 1.9 repeating is equal to 2, and that would be a no-go. And 2 wouldn't make this true, and anything bigger than 2 wouldn't work. So the way we denote this is with an open circle at 2 and shade it to the left. Yeah, again, that's why it's a recall. Isn't it great? Because you've hopefully seen this before. I've seen this before. Hey, I heard that call before, is what SpongeBob says when they blow the little flute thing, whistle thing, and it says, loser, loser. You know, when they made him jellyfish bait. You know what I'm talking about. Yeah, everybody loves pie. So, so what this open circle means is that it is every point up to, but not including 2. Interesting. So let's look at one more of these. What if I had us graph x is greater than or equal to -3? So let's draw us a nice little nombre line. It's good to know where 0 is. -3 is to the left of 0. And I'll throw those couple of tick marks in here this time. Now let's see, what's the solution? Is -4 a solution to this?
No. Yes.
Is -4 bigger than -3?
No. Well, yes, it is actually.
Is it?
Yes.
Why?
No.
Because
Well, yes, it is bigger.
it's further to the left on the number.
It's actually smaller than negative.
So are bigger numbers this way?
No, bigger numbers are towards 0.
Bigger numbers are to the right,
Yes.
right? This is where numbers like 10 or a million would be, right? Or like 10 to the 100th power, which is Google right there. Stuff like that, right? 10 to the 81st power is the number of atoms in the universe, roughly. Stuff like that. So yeah, bigger numbers are to the right. Smaller numbers, -4 is smaller than -3, okay? So -4 would not be a point there. We wouldn't like that one. Does -3 work?
Yes.
Because it has the or equal to part. So -3 we're cool with, yeah. And any point to the right of that would work. So this one, what we would do is put a closed circle or filled in or shaded circle because it includes it. Yeah, it's got the equal to portion. And it's shaded to the right because all the points bigger than that are to the right. And notice 0, for instance, is bigger than -3. Right? So if you've experienced debt, getting back to 0 and being broke is actually a good thing instead of owing, say, I don't know, hundreds of thousands of dollars. That would not be fun, I imagine, anyway. So that's some recall stuff that I wanted you to think about there, just because some of this is going to come into play today when we're solving inequalities. But the first thing I want to talk about before that is this thing called the trichotomy property. Trichotomy property. There we go.
Didn't we talk about this like 2 minutes ago?
We did. Yeah, I mentioned this briefly. That I did. And what the trichotomy property says is the following.
It's a real number.
Oh, wow, man, you're falling down a rabbit hole asking that question. For any two real numbers, for all intents and purposes, any number you've experienced up to this point has been real. But there will
Except for
be...
that one you just showed us that was 0.0.
Well, but that one wasn't even a non-real number. Yeah, don't worry about it. We'll figure it out later. Yeah, we'll have non-real numbers later on in this course. It'll be great. Good stuff. So it says, for any two real numbers, A and B, exactly one of the following statements is true. So either A is less than B, A is equal to B, or A is greater than B. Cannot be multiples of those true at the same time. Okay, so that's good stuff. That's good stuff. And yeah, and we talked about that a little bit earlier with 0.9 repeating related to 1. And then it turns out another thing we should know is the addition and subtraction properties. And we've had the addition and subtraction properties of equality, but this time we're going to have of inequality. And let's see, I'm not going to have you write down this first part, but I will explain it. But I will have you maybe summarize the second part here. Oh, you need me to go back real quick?
Just 2 seconds.
2 seconds there. So, addition and subtraction properties. I just spelled properties wrong, guys. That's sad. Properties. There we go. I'm going to fix that. Properties of inequality. All right. Don't write down this first part with the 1 and the 2 here. All right. That won't be necessarily helpful to you. Well, it'll be helpful for us to look at. But yeah, the second statement might be valuable to know. It says, for any real numbers A, B, and C, if A is greater than B, all right, then I could add C to both sides of that, and it would still be a greater than relationship. Okay? That makes sense? Or, and rather, for the subtraction part, I guess, I could subtract the same number from both sides, and it would still be a greater than relationship. Okay, makes sense, makes sense. And then similarly, if A is less than B, you could add C to both sides or subtract C from both sides and still get the same thing. Good stuff. So, so that is the addition and subtraction properties of inequality. And I summarize it saying you can add or subtract the same number to both sides of an inequality without changing the inequality. Right? So if I have an already unbalanced scale and I add a watermelon to both sides, the scale will still be unbalanced even though those two watermelons weighed the same amount. All right, that's the idea. So let's put this to work. Why not, shall we? Put it to work. So let's do an example. Example. Saving the day. It's gonna be great. Here we are. Is it? I don't know. What did I do? So let's solve the following. 6x plus 3 is greater than 5x minus 2. Huh.
Can you go up to that again?
Yeah. Real quick. So 6x plus 3 is greater than 5x minus 2. Now, for all intents and purposes, let's more or less pretend this is an equal sign here. What would you do to both sides if we were just solving an equation?
I'd subtract 3. No, actually, I'd add 2.
Would you?
No, you would add 5. Or add
Yeah.
Okay.
Technically, you're not wrong for wanting to move these around, but I'd actually recommend dealing with the x's first, because I don't know which side. Do I want the 3 over here, or do I want the 2 over here?
Well, I want the 2 over there to keep it positive.
But I actually don't care about the non-x parts. I just want to move them away from wherever the x's are, right? So once I decide what side to move the x's to, then I'll just move everything else away from it. But so that's the first thing I have to decide is where am I moving the x's. So,
How do you know?
well, for the x's, I'm going to bring the little guy to the big guy. So I'd subtract the 5x from both sides. And we'll have 6x plus 3 is greater than negative 2. All right, and now that I've got all the x's on one side, now I know, okay, it's the 3 that I want to move, not the negative 2.
Oh, wait, you get 6.
Oh, blast! You're right. Oh, you guys saved me there. 6x minus 5x is 1x. Classic. That's why you got my back. Thanks, friends. We're mathing this together here. So now what do I do to get x alone? Subtract 3, right? Subtracting it would undo the adding of 3. And those would cancel out. I'd get x by itself, and x is greater than negative 5. Those became more negative. And there we go. And if I wanted, I could even graph this. All right, so I could draw a number line of the solution, which I think there might be some points in your book where they ask that for the homework tonight. I don't recall. But x is greater than negative 5. Is that going to be an open or closed circle? Open, because it doesn't include 5 itself. And am I shading to the left or right?
Right.
To the right, because the points that are bigger are to the right. And actually, this works most of the time if you have x on the left side and your thing you're relating it to on the right side, that the sign, the greater than sign, almost looks like an arrow telling you what way to shade.
Oh.
And if it was a less than sign, it would tell you to shade to the left. Pretty good stuff. So you could actually also relate less and left. So I try to think of all sorts of ways to remember, remember things like that. So that way I don't mix it up, So check this out. If I wanted to determine whether or not I was right, if I wanted to do a quick check, I could pick any point in the shaded region and plug it in for x and just make sure, did I do this right? Or it would actually kind of just verify a little bit, not entirely. All of the stuff I could, still make some mistakes. I guess that would be within a tolerance there. But what's the best point to plug in from the shaded region? What's the easiest number to do math with that's part of the solutions here?
1.
1 would be pretty good. I like 1, but I'd say even better than 1. How about 0? 0 is like the coolest number to do math with because math just becomes super easy with 0. So I'm going to plug in 0 from my shaded region into the original problem real quick. So 6 times 0 plus 3, is that greater than 5 times 0 minus 2? What's 6 times 0?
0.
And 0 plus 3 is just 3. Is 3 greater than 5 times 0 is 0 minus 2? Is 3 greater than negative 2?
Yes.
And that is a true statement. So that kind of verifies for me that, okay, I shaded in the correct direction. And it gives me a little bit of confidence in my answer anyway. It's still possible I made some other mistakes sometimes. So that's not bad. That's not bad for solving. So you could subtract things. I could have even, if I was adding things, this all would have been great. You can do that using this property, and it doesn't change the fact that this inequality symbol is the same. So let's consider the following. Consider. We'll do a little two-case analysis here. Let's start with 4 is greater than 2. Is that a true statement?
Mm-hmm.
Yeah, okay. Let's do some analysis with multiplication. What happens if I multiply both sides by 3?
Pretty sure it's gonna still.
I get 12 and 6. And is 12 greater than 6? Yeah, that's true. Good stuff.
Always gonna work if you multiply
I just
by
spelled
the
true
same.
wrong. I wrote T-U-U-E. That's weird. True. Okay, so let's do another analysis. 4 greater than 2. And this time let's multiply both sides by negative 3. And I'm going to get negative 12 is greater than negative 6. Is that true?
No.
Negative 12 is, I wouldn't want to have $12 of debt, right? $12 of debt is worse than $6 of debt. That's not greater than, that's less overall. So this is false. False. However, notice this, negative 12 is less than negative 6. The reverse statement is true, right, if I flipped this sign. And it turns out that there's an interesting property going on here with multiplication and inequalities. If you multiply by a positive, you're cool.
If you multiply it by a negative, you just switch the sign and then it's equal.
I like it. Yep. So let's summarize that. We'll call this, and it turns out division has the same thing. Multiplication and division. Properties of inequality. And they land in the same boat because dividing is the same as multiplying by a reciprocal. So oftentimes when you find a property of multiplication, the property of division is very similar to that. Oftentimes. So let's see. And I'm going to summarize this with the following statement, which is going to be this. Which says, whenever you multiply or divide each side of an inequality by a negative, flip the inequality. Flip it. Flip the inequality. That's not too crazy. It seems to make sense. So, I mean, as far as our experience with inequalities, they basically behave identical to equations, right? I can add things, I can subtract things, I can multiply, I can divide. The only thing I have to be careful of is multiplying or dividing by a negative. All right, that's the only time I have to watch out. All right? Otherwise, it's all the same. So let's try an example of this. I like my little intermission music. It's like, come on down, try this problem. Little game show music, I like it. So let's see, if I want to solve this inequality, 2x plus 6 is less than 10. What do you think I should move first? How could I do this?
Add 6.
Add 6? Adding 6 would kill a...
Subtract 6.
I want to do the opposite. I like it. Aha. Because I got to undo that, right? I want to make sure that adding 6, notice, would actually cancel out with subtracting 6. But if those were both plus, I'd get 12 over there, and I would have not gotten any closer to solving. So let's see, I'll have 2x. Let's see, do I have to flip the sign? This was negative.
No.
No, why not?
Because you got 2 negatives.
Because I wasn't multiplying or dividing. I was just subtracting, and subtracting's fine. 10 minus 6. Let's see, signs are different, so I subtract them. What sign do I keep? The positive, because 10 was more influential. All right, here we go. How do I get rid of this 2 in front of the x?
Divide by 2.
Because it's multiplied. I'm dividing both sides by 2. X is less than 2. Yeah, so that's another common thing that will very easily go back to our equation nature, and we'll just be like, start throwing in equal signs there. So just make sure that you're transcribing from right sign to sign here the proper thing. And I got x is less than 2. Wait a minute. I didn't have to flip the inequality?
You did not.
I did not.
You're not dividing by a negative.
Because I was dividing by a positive 2. This is only applying if this was dividing by a negative. Question?
Were you talking to me?
No. What? What's your question?
Can I ask my question?
Sure, sure.
Okay, so how do we, like, because the one that we just did with adding and subtracting, how do we, because we just kept the other one,
Well, I subtracted here, and I ended up not ever having to divide or multiply, right? Because this ended up conveniently having a positive 1 coefficient.
Oh, so if that was like 2x, then you'd have to still.
Then I would have had to divide or something like that. Yep. Yep. What was I going to say? Question, side note, what if I had this? What if this was a -4 the whole time? Would I have had to flip the sign?
No.
Why not, Tyler?
Yes.
Oh, yeah.
No, because you're not actually dividing it by a negative. It is a negative, and you're dividing.
Right,
it by
I'm dividing a negative by a positive 2.
So that's fine.
So I wouldn't have to flip it. So just as kind of like a little case study for you to be aware of, it's only the thing I'm dividing by, the yellow work step that I'm showing. If that's negative, then you flip it. Otherwise, we're cool. Okay, so let's try un otro example here. Moving right along. I like this. Let's see. Oh dear, what did I just do? Oh dear.
Is this the multiplication?
Well, this is going to be using all of them. Good stuff. All right. Crazy sauce. Now, what do you think we should do here?
First thing we're going to do is divide by -2.
We can do that. We absolutely can. I like that start. That's fine. Or
Distribute.
you could distribute. Now, if these were absolute value, would I have been able to distribute? No, and I would have had to divide by -2. So either of those techniques work. In fact, Moro, if you want in your notes to do the divide by -2, that's fine. I'm going to do this distribution just because I like distribution sometimes when I can do it. So -2 times 3x is -6x. -2 times -4 is +8 is greater than or equal to 12.
Now we can add 8 or subtract 8. Jesus.
Ooh. Hey, yeah, it's okay. It's okay. You caught your mistake there. It's good. So inverse operation. So -6x is greater than or equal to 4. Yeah, and then kept the sign of the positive. I like it. Let's see. Now what do? Do I add 6 to both sides?
I'm going to divide by -6.
Emily, why aren't I adding 6 to both sides?
Because you're just keeping it.
No, because 6 is multiplied by x. So
Because that's a little multiplication there. So the only way to undo the multiplication is divide. So I'm going to divide both
I was
sides.
just thinking about how you can't put x and 4 together.
Right. Yeah, that those weren't like terms, or
Yeah.
sure. So let's see. Dividing by a wait. Did I just say divide and negative in the same sentence while I'm dealing with an inequality?
Does that mean you flip the sign?
Yeah, I think so. I flipped that inequality. Bam. Flip it.
you get x is less than or equal to 2/3.
Oh, and he reduced that 4/6. 2 went into both of those. 2 goes into 4 twice and into 6 thrice. And what about the sign? Is that positive or negative here? Positive divided by a negative is
Negative.
still negative, yeah. So x is less than or equal to -2/3 is our answer.
Boom.
So, little side note, we div by neg, comma, so we flipped.
Div by neg abs val, so we flip.
Bam. Good stuff. Let's try one last example and we'll call this lesson done. I think that sounds good to me. Ooh, I like it. So let's see. Let's get an example in here. Bam. Paste. Whoosh, whoosh, right there. That looks like a good size right there. I like it. So, -5x plus 7 is greater than -2x minus 9.
I say that we combine like terms first.
Combine like terms, so like the
Add
So the
x.
x's.
So I can just combine these?
We are going to
Add
no.
x.
Oh wait, I have to move them because they're on different sides of the relationship, right? So I can't just combine them. I have to move one. Which one should I move?
5x. No, 2x. Sorry. 2x.
Which one's smaller?
The two.
Well,
5x.
-5 is technically smaller. Now, if you moved the -2x, that's fine. You wouldn't be wrong. We would just have a negative show up, and that's fine. There's nothing wrong with that. I just happen to be a fan of always moving the little guy to the big guy to avoid negatives if I can. Right. So I wouldn't mark you wrong if you added 2x to both sides there, just so you know.
It just makes all the math easier.
A little bit. So let's see. Here's my main problem right here. My 7s and my less or greater than signs sometimes look similar. There we are. Let's see. -2x plus 5x is how many x's?
-7.
Let's see. Well, their signs are different, so we'll subtract the numbers. 5 minus 2 is 3. And whose sign should I take? Who is more influential? It's positive because the 5 was more influential than the 2. Okay, good. -9. So, let's see. Did I have to flip the inequality there?
You did not.
Because I'm adding. Even if I was subtracting, I would have been fine, right? Okay, let's keep going. What do I do now?
I'm going to add 9.
Add 9 both sides. I like it.
You have 16 is greater than 3x divided by 3, and you get x is less than 8.
Ooh, go. No.
Sorry, greater than.
Well, let's see. This would be 16/3 is greater than x. But I wouldn't like to write it that way. And I like that you were automatically flipping it. So I would like to write that as x. But if I'm flipping this whole thing,
You gotta flip the sign.
yeah, the sign's flipping with it. And that's what you did do correctly, right? You said x is less than. And then you said 8, but that was just because you made an error there. It's 16/3 won't reduce. But I think you were doing 16 divided by 2. But you did get the more important thing of this when you flip an entire inequality. I'll call it an ineq. The sign flips too. Not flips, not slips, but flips. There we are. There we are. There we are. So when you flip an entire, that's a weird looking R there, entire ineq, the flips too, man, guys, I didn't even write words. What am I doing? The sign flips too. I said it out loud, kind of. There we are. Haha. Excellent. So, I'll leave it this time. Fine, there we are.
How you do your exclamation points.
Yeah. How do you guys do it? Do you go like top, down, and then dot? I like kind of the dot and then like bam. It's just like I'm ending on like the more dramatic point, I guess. There. Anyways, thanks for watching, internet friends. Hopefully you learned a thing or two about ineqs, and I'll talk to you later. Bye-bye.
Bye, internet friends.
Bye-bye.